Okay, we're going to look at something called the astronaut oxygen problem and illustrate how to compute the expected value of a continuous time Markov chain at some point in time in the future. Here is the setup. So the way this is going to work is that picture an astronaut approaching a space station. So the astronaut is first outside in outer space. And to enter the space station, the way it would work is that the astronaut would first enter a chamber without any oxygen. And this chamber is closed off from the rest of the space station, which is going to be located on this side here. This chamber is connected to another where there is oxygen, and it's sealed through a door, which once the astronaut fully enters the chamber, so once they're fully in here, the door here would open, and then oxygen would begin streaming in until we reach some sort of equilibrium. And once that equilibrium is attained, then the astronaut can go ahead and proceed directly to the main part of the space station. So we're going to use the Ehrenfest model for the for the dynamics of these oxygen particles. And let's revisit the discrete time case first, just to review. I'll set up the continuous time model in a second, but if we're just talking about the discrete time case, there are n particles of oxygen. Let xk be the number of oxygen particles in the right chamber at time k. It used to be the left, but might as well be the right. The state space is 0 to n, so you could have 0 particles in the right, all the way up to n particles on the right. The possible transitions in the Ehrenfest model were we can gain a particle or we can lose a particle. And these had probabilities. Assigned to them. Here is the probability of this transition here. So let's look at this probability very quickly to review. It's a probability of transition of gaining a particle. So the dynamics work as follows. We pick a particle at random and move it to the other erg. So here, we're going to have to pick a particle on this side and move it over here in order to gain a particle, right? In order to have this transition. And this happens with the probability of selecting a particle on the left. The number on the left was n minus x, and therefore you get this transition probability. For the other transition probability, to lose a particle, you had to pick a particle on this side, supposing there are some, and x is the number on the right. So if x is 0, as there are currently, then the probability of losing one is obviously 0. That makes sense. But if there are a positive number of particles on the right, then the probability of picking one of them is x over n, which would then move it over to the left, decreasing my particle count and giving us the probability of this transition. And again, in this problem, we start with x0 equal to 0, so 0 particles on the right, and we had all sorts of calculations. One of them had to do with the stationary distribution. Here it is. This is what happens after a long time. The probability of having x particles of oxygen on the right was given by this counting formula, the way to actually rearrange x particles on the right and n minus x on the left. And from here, you can easily verify that this process is reversible by verifying local balance with this stationary distribution and these transition probabilities. The process is reversible, and that means that potentially from equilibrium, we could go all the way back to the beginning. The beginning was x equals 0, so there should be some chance of a spontaneous reversal, where this is a picture indicating that's not a good thing. And this represents a scenario where all of a sudden we've reversed back to the original starting state. And of course, the probability of this is very small. If you plug in a 0 into the stationary distribution here, you will get 1 over 2 to the n, which is a very small number for n large, which it is. The number of particles of oxygen is very large. And the other calculation that we did involved first step transition analysis, which means that we're computing the expected number of oxygen particles at time k, and that was given by this expression here. As k went to infinity, this term became negligible, and not surprisingly, at equilibrium, we expect to have half the particles on the left and half on the right. So we're now going to have to think about what all this means in continuous time, and I'm going to show you how to run this calculation. How do you get the expected number of particles in a continuous time setting? So let's first go over the setting. So we have these n particles of oxygen. Imagine that each one of them has a clock. So it has an exponential random variable eta I of rate mu, each one. All of them are independent clocks, and we're going to run these clocks, and one of them is going to win. So one of those exponentials is going to kind of arrive first, and we're going to pick that particle. So we're going to pick the j with the smallest eta I, and we're going to move it to the other chamber. And of course, there is this memoryless property of the exponential distribution, which is going to allow things to just kind of restart as if nothing happened. So all the clocks get not reset, but they're automatically reset by this memoryless property, and the dynamics continue onward. If we're going to let xt, we're now in continuous time, be the number of particles in the right chamber at t, our goal is to compute the expected number of particles at time t. I'm going to use this using first step transition analysis, whatever that means in continuous time. But first, let's construct the Markov chain, and I'll show you what this would entail in a bit. So the state space must stay the same, of course. The fact that time is continuous is not going to change the fact that the number of oxygen particles is discrete. And the first thing to look at is this the winner of all of these clocks. We have n particles, each one has a clock. We're going to look at the very first one. So this is going to be the particle that fires first, the particle that wants to switch chambers first. We've already seen this calculation. The minimum of n exponential random variables is an exponential random variable with the rate that's the sum of the rates of the individual ones in this minimum, so the individual eta I. Each one has rate mu, so we sum up over them to get mu n. So we know that the next time that a particle, not any specific particle, but some particle, switches chambers is going to be exponential with rate mu n. And so now, given that the state space is S, we know we're going to change from any number x either up one or down one, and that's going to happen with rate Rx, completely all the same for all states x at a rate mu n. You can extend this analogy a little bit further and say that what's the chance that it's the particle on the right that's going to win. So one of the particles on the right that's going to win. How many of them are there? There are x of them. So we're looking at the minimum of x random variables. Each one of them has rate mu, and so therefore the rate of events happening on the right, so particles being selected on the right, is equal to mu x. Same logic for the left chamber. There are n minus x particles there. The minimum of their clocks, so we have n minus x clocks, each of rate mu. The minimum of those is going to be exponential with rate RL equal to mu times n minus x. So same exact logic as up here. And now we have two clocks, one for the left chamber, one for the right chamber. And they're competing for the next event. We want to know, in other words, when do we go up and when do we go down? So when do we gain a particle? When do we lose a particle? So here's the probability that the clock on the left wins. If the clock on the left wins, that means that the particle on the left fires and is moved over to the right. So this corresponds to the event of the transition where the particle from the left moves over to the chamber on the right. We've seen this calculation again. What's the probability that one exponential is less than the other? You put the rate of the winner up on top, and you sum the rates on the bottom. So just expanding out and substituting RL and Rx gives me this, which should remind you of the Ehrenfest probability. So that problem was set up in a very convenient way, or the natural way. That's why we picked this expression up once again. And the summary of this is that the probability of the embedded chain, this is what we're looking at now. We're looking at, we know how long time passes between each event. It's going to be this rate here. This is the rate in every single state. Then some event is going to occur, and there are two types. One is the gate particle, and that's going to be happening with embedded chain probability n minus x over n, right here. And the other one is we lose a particle, and that's going to be happening with probability x over n. And these were not sort of determined outright. These were deduced based on properties of these exponential clocks. So, the summary is that every particle has a clock. The winner gets selected, and this leads to these probabilities. This one's saying a particle on the left wins or the particle on the right wins. They correspond to these two transitions and give out these two very natural Ehrenfest looking like probabilities. So our embedded chain is now summarized like this. And here is the kind of full summary of what happens here. X is modeling the number of oxygen particles in the right chamber. It is a continuous time Markov chain on this state space. It has a rate for every state given by mu n. So this is the rate of events that are occurring. So this is giving you the rate at which some particle is being selected and moved over to the right or left, depending on where it came from. And the embedded chain tells us how the transitions actually happen. So we pick up an event with rate mu n, and the embedded chain is going to tell us which state we transition to in this state space. Another way to write all this down is in terms of the generator, which can be translated directly from the transition probabilities. So you have this generator matrix for this problem. The rate of transitioning to x plus 1 from x, this is gaining a particle, is going to be proportional to the number of particles on the left. And the rate of losing a particle is proportional to the number of particles on the right. And then, of course, the generator at xx is negative the rate of that state, which is mu n. So you can almost see, almost feel an interpretation for this and how it makes sense. If there are a lot of particles on the right, then there's going to be a lot of pressure for them to move over to the left. And then conversely, if there are a lot of particles on the left, if n minus x is large, then there's going to be a large rate pushing them over to the right chamber. This is the transition rate diagram for this process here. So you can just kind of read it off. State 0 means 0 particles on the right. And in that case, there's going to be a very large rate of gaining at least one particle in the next move. And that rate is mu n. So all of the particles on the left are all sort of competing for which one is going to make a move over to the right. And that cumulative rate is mu n. And then everything else that I wrote down in between corresponds to all of these calculations that we've already done. So in particular, any given state can move up or down depending on the rates prescribed by the generator here. So this is called the birth and death chain. Your book has a lot of analysis for this, and we're going to do something that's actually missing in the book, which is compute the expected value. We're looking at the expected value at time t in the future, starting from any state x. So we could start from 0, but here I'm going to start with an arbitrary state x. And here's how the calculation is going to go. So the first thing to do is write down the formula for mx, which is nothing other than taking the involved probability distribution. What is our probability of going from x to y in t time steps? And integrate it or sum it up against the possible values. So any value potentially could happen in the future. So we could have y particles, any number of y particles at time t in the future. And we're going to multiply by the transition from the starting state x right here to the final state y in t units of time. So that's going to be an expression for the expected value. Next part is easy. It may not be intuitive as to why we do this, but I'll show you in a second. The goal is going to be to use the Kolmogorov equations, and for this reason we're going to take a derivative of both sides here. So I now have the derivative of m equal to the sum. Y doesn't depend on time, so I skip it, and I just take the derivative of the transition probability. The reason for doing this is to use Kolmogorov's equations, which are right here. This is the forward equation. And now I can plug in this here expression for the derivative. Here it is, coming into the original formula, and now I'm just going to exchange the two sums and rearrange the terms a little bit, and I'll show you why this is the case. What this is really amounting to in terms of a first step is sort of an instantaneous step. So I'm splitting up not over one step, which we would do in the discrete time case, but now I'm splitting up over so the transition up to time t times an instantaneous final transition into state y. So that's sort of the intuition, and that's what it means to perform a first step transition analysis in continuous time. And now let's keep going. We're going to take this sum, which we're going to have to unpack. And the way to unpack it is to see, which terms are positive and which terms are zero. So the ones that are, the terms that are not zero are these ones right here. And so that we're summing up overall y, and we have to ask which things in the sum are actually going to give you something that's not zero. And, in here it's, pretty clear. We have to go from, transition has to be of the form zy. So what can y be? It can be z minus 1, it can be z, and it can be z plus 1. Those are the only non-zero transition rates according to our calculation on the previous slide right here. Okay. So we plug all of these in, and of course they have to be plugged in by adding the corresponding value of y. Here y was set to be z minus 1, then it was set to z, then it was set to z plus 1. And now all I have to do is plug it in. The quantities, these rates essentially are coming directly from the previous slide. And once they're plugged in, it takes a little bit of time to simplify, and you can check my calculation, you get to here. So this is a complicated sum, but because the transitions, the non-zero transitions are limited in number, we're able to really simplify the problem. And all of this really has the same feel as first step transition analysis in discrete time. And now we're going to put everything back together again. This is the what happens when you plug in to this formula, or I guess rather this one, plug in this final sum here. And so this probability stays. It is right there, and that sum that's left over is left over here. Now what you can see is that the first term in this difference doesn't depend on z, and it's just a sum against these probabilities, which better sum to 1, the probabilities after all, so you get mu n. And the second term leaves mu times this sum, and if you look at the sum, you'll recognize something curious here. That sum is really just the expected value. So we've defined mx to be the expected value at time t starting at x. We were able to get to this point, and now we just recognize that this whole part here is just nothing other than mu times the original expectation that we sought. It's the sum against the probabilities times the possible locations of the particle. Before it used to be labeled y, now it's labeled z, but it's the same formula. And you can check by differentiation that this happens to be the solution, which should remind you of something very similar that happened in discrete time. So here, as t goes to infinity, we again see that the number of particles in equilibrium will not surprisingly be n over 2, and this will happen really quickly. The rate of convergence of this to the equilibrium is exponential rate mu, in fact. So right here. So the faster the particles move, the faster we converge to the equilibrium configuration n over 2, or what the average sort of distribution of the particles is in the end. You can try to look for all sorts of connections with discrete time, which there are a number I won't discuss, but roughly they all go through this formula here. You can take anything that looks like this, and with the right scaling of time, approximate the exponential this way here, and this would happen for large time. And so the more natural way to really do this is to take the modified Earn example, where with the probability Q you actually leave the particle in the same place where you picked it from, and that Q can actually be shown in a natural way to be related to the rate mu at which every single particle moves. So if you're interested, I'll let you kind of explore these connections on your own, but you can definitely see a pretty significant degree of similarity between these two formulas, and that's not that surprising. So I'm going to say one more quick word on the spontaneous reversal scenario. One could ask, what is the expected time to which this happens? So that calculation is difficult, but at this point you have enough tools to really dig into this calculation. So I'll leave you with a reference. Something like this was computed in this paper, recurrence time for the Ehrenfest Earn model. They do mean continuous time, so this is in the continuous time setup of the model, the same as this astronaut problem. And the authors are Bellman and Harris. You're welcome to look up the paper, and I think at this point you have most of the tools to understand most of that work, even though it's still not that simple. And I think this paper is 1951 or 1961. I don't quite remember the year, but I'll let you kind of explore it on your own, and that wraps up this clip.